going to, we may not get through all this today, but we'll get as much as we can done. We use integrals for, whoa, that's kind of weird. Let's try that again. We use integrals for many, many ideas. As we had suggested in the previous lecture, we use them to look at changes related to rates. One of the other things that we do with integration is to find areas under curves. Now we're going to expand that idea to include finding areas between curves. So that light blue area, we'd like to find the area, we'd like to find its area. We'd like to find how much area is in between those two curves from A to B. Now, to make an analogy, when we did area strictly below a curve, we drew a picture that kind of looked like this. And then we said, oh, here's A, here's B, and there's the area that we're interested in finding out about. But then we started saying, but we need to conceptualize the area between the curve, and we get back to this idea of the Riemann sum, that we break up this area into a bunch of rectangles. And they could be right-hand rectangles or left-hand rectangles. We might use a Simpson approximation, but the true integral was based on breaking it into rectangles, making the number of rectangles more and more and more. Each rectangle got smaller and smaller and smaller until we get the area under the curve. We started with the idea that if this is the function f, that the function of f x sub I star times delta x, and if we add all those rectangles up, we got an estimate of the area. And then we said if the number of rectangles went up, the limit of n approaches infinity with n number of rectangles, then we got the area. That's all review, and that was the basis of what we built the integral expression out of. The new stuff, though, how's it the same? How's it different? How's it the same? How's it different? How can we look at this particular expression and its components and say, how is it going to be different for this particular case? Well, in order to do that, I want you to start visualizing, as I clear the drawing and I move forward, that we're taking that space between the curves, the space that we're interested in finding the area of, and we're breaking it up into rectangles again. Now those rectangles have height, those rectangles have width, and what would we call each of those things if we had to go back to this expression of multiplying some expression times some expression? Let's take the easy one. Let's take the width. In the previous example, height just under a curve, area under a curve, the expression of the width of each rectangle was represented by delta x, which I might call a slice of x. In the previous example with areas under the curve, the height of each rectangle was just f of x. But is that the case now? Is there some way that we can express the height of this rectangle as it's bounded on the top by the curve f of x and on the bottom by the curve g of x? Could it be f of x minus g of x? Is that true? For some particular x, f of x minus g of x would be the height of that rectangle? It's absolutely true. So, if f of x minus g of x for some particular value in that particular interval will give us the height of the rectangle, we end up getting an expression then that will represent the area between the curves. Now, this is all written with really big, thick slices. Okay, big, thick slices, like Buddy's pizza-sized slices. Let's get it down to smaller slices. when we break it down to smaller slices, we no longer talk about delta x's anymore. When they become infinitesimally thin, we no longer refer to it as a delta x, we refer to it as the differential dx. And instead of using sigma and adding up all the rectangles, we have a different symbol for adding up the infinite number of rectangles as those slices get thinner and thinner. And that is the integral. So sigma gets replaced with the integral symbol, delta x gets replaced with dx, and inside of here, we get f of x minus g of x, which leads us to the conclusion of this slide, that the area between the curves of f of x and g of x are continuous, and f of x is always larger than g of x. Then the area between the curves of f of x and g of x from a to b is equal to the integral expression from a to b, f of x minus g of x dx. So the conditions are f of x and g of x continuous, and the top curve minus the bottom curve. Top curve minus the bottom curve. Top meaning with higher y values, and bottom meaning lower y values. By the way, if f is always larger than g, then f minus g is always a positive value. If the limits of integration go from a low number to a high number, the differential dx is always a positive value, and this particular expression will always return, this integral will always return a positive value. Are we ready to go and apply this newfound knowledge to a problem?
Yes.
You betcha. That's a Minnesota. I'm getting in the Minnesota mood.
Yeah, that's what I said.
Well, I heard it long before Sarah Palin. I heard it associated with people from Minnesota.
Oh my God.
Like if you ever seen the movie Fargo,
Yeah.
They do talk.
they talk like it, and that's exactly the way they talk.
That's how my godmom
She's
talks.
from Florida. That's such a weird
Fargo's actually in North Dakota, but the majority of the movie actually takes place in Minnesota. All right, let's move on.
Is that a Joel and Ethan Coen movie?
Yeah, it sure is. Actually, I just heard a very interesting interview with Joel and Ethan Coen about the making of True Grit. All right, so I would like to find the area of the region between y equals secant squared and y equals sine from x equals 0 to x equals pi over 4. Now, before we can actually set up the integral that does that tells us this area, well, the previous slide said that we have to make sure to list the curve that's got the higher values first and the curve that has the lower values second. We can't do this unless we know what curve's on top and what curve's on bottom. So let's draw a little picture. What does the graph of secant squared look like? If I remember correctly, secant squared is undefined at pi over 2 and negative pi over 2. I think it comes down all the way down to the value 1 and essentially runs like there. And if we went over here, it runs like that. It goes back and forth that way. So there's secant in blue. What about sine? Starts here, and by the time it gets to pi over 2, it gets up to 1. Is that right? So the area that we're specifically talking about is this area right here. The area between secant squared and, oh, I'm sorry. I drew secant, not secant squared. Secant squared is never negative. Kind of looks like that. All right. But I'm still convinced that secant squared has always got larger values than sine squared, at least on this interval. So let's write that integral expression, which is going to represent the area between those two curves. Well, secant squared on top, sine on the bottom. Limits of integration? 0 to pi over 4. And let's see what we can do with that. Antiderivative of secant squared. Tangent. Antiderivative of sine. Negative cosine, I think. I always get those mixed up with the signs. Antiderivative of sine, negative, okay. And then we're going to evaluate this from 0 to pi over 4. Don't like negative signs, but we got two of them, so they cancel out. Looks to me like I've got the tangent of pi over 4 plus the cosine of pi over 4 minus the tangent of 0 plus the cosine of 0. Tangent of pi over 4 trips off the tongue. 1. Cosine of pi over 4, root 2 over 2, minus the tangent of 0, 0 plus cosine of 0, which is 1. So I end up with 1 plus root 2 over 2 minus 1, which is equal to root 2 over 2. Hooray! So aren't you glad I gave you secant squared though, right? That made that antiderivative a little bit easier. How about we try something a little trickier? The area in the region enclosed by the parabola, or I once heard it pronounced parabola. Well, no, in India, I guess they actually say parabola. It's just how they pronounce it. What?
Instead of hypotenuse, they say hypotenuse.
That's a cool pronunciation.
Well, I know that they say, instead of saying aluminum, they say aluminium.
I thought that was like an England thing.
Well, I think it's because they use a British form of
Right.
a British form of English as compared to our version, which probably can't be really called English anymore.
Americanized English.
American English, I guess.
Or just American.
American, by God. All right. So what's the first trick to doing these area between the curves problem? We got to be able to visualize what the space looks like, what the region looks like. So what does the parabola y equal 2 minus x squared look like?
Upside down. Parabola, so that's
Vertex at 2.
upside down.
It's really funny. We use expressions like upside down. Like when you encounter parabolas in nature, they're always this way. But here's this upside down one. I mean, trees could be upside down, but I don't think parabolas have that distinction. I mean, if you spray water into the air, the water then breaks up and forms a sort of a parabolic as it falls. So maybe this is the natural way parabolas are. And maybe these are the ones that are upside down.
What we live in plastic,
I thought lived in a Barbie world.
Nice squirrel.
All right, so we got the parabola, the parabola. Okay, what about that? What about y equals negative x?
It's a line from the slope.
Like that?
Yeah.
Okay, and that line crosses the parabola at those two places. Now that's going to end up being significant because the area that we're interested in is bounded here and here. Essentially, that intersection point is going to help define our lower bound of integration, and this intersection point is going to define our upper bound of integration. So, the area between the curves is going to be this integral from A to B. Upper curve is going to be 2 minus x squared, and the lower curve is going to be x squared. Watch out for all those negative signs running around. They're going to do us no good. Okay, we're great. What is it?
I don't understand.
How can we do this problem?
Find out where they
We're going to have to find out what A and B are.
A is negative.
Yeah.
Set
A is negative 1. For K.
Because when you first draw the two, knowing what the spaces for you draw the parabola and then whichever order you do it, just that point right there where
I've got a great idea. Instead of saying it's negative, A is negative 1, let's find some sort of analytic, algebraic methodology that will help us define the intersection points.
Set them to equal to each other.
What does them modify?
Two equations.
The two equations. How about y equals y? Oh, does equal y. That's a tautology. How about the other ones? How about 2 minus x squared is equal to negative x? All right. Because at this location, both x and y are equal. So it's true to say that this y is equal to that y at that intersection. So the other sides of the equations must be equal as well. Any ideas of the methodology to find the values of x that satisfy this equation? Get x all on the same side. So how about 0 is equal to x squared minus x minus 2?
X plus 1,
X plus 1, x
x minus 2.
minus 2?
No, wait, is it?
Because when they multiply them together, it's going to be a negative?
Are you adding the x to get it to 0?
No, the negative x is already on that side.
Negative x is, so I brought this over and it became positive. I brought that over, it became negative. This one was already over there, it stayed the same. I think that's the factorization. And it does confirm what Edmund said, that x is equal to negative 1. And it tells us what b is as well. B is 2. So we have confirmed that A is negative 1 and B is 2. So now we can finish off our rewrite from negative 1 to 2 of 2 minus x squared and plus x dx. Excellent. Now what? Anti-differentiate. Help me out. Do the first one for me, Jordan.
2x.
2x. Who's got the next one? Minus x cubed over 3. Let me take the derivative of that. Bring down the 3. 3's cancel. X. Yep, sounds good. And who's got the last one? Plus x squared over 2. As evaluated from? Negative 1 to 2. Are we ready? plug in the 2's. 2 times 2 minus 2 cubed over 3 plus 2 squared over 2. There's our upper end evaluation. Minus 2 times negative 1 minus negative 1 cubed over 3 plus negative 1 squared over 2. 4 minus 8 thirds plus 2 minus negative 2. Negative 1 cubed is negative 1 plus 1/3 plus 1/2. And if we distribute this sign through here, we get those signs. Let's total it up. 4 plus 2 is 8. 8 thirds minus, negative 8 thirds minus another 1/3 is negative 9 thirds, which is a minus 3. And then we've got an errant 1/2, negative 1/2 running around there. That's 5 minus 1/2, 4.5, or 9/2. And
It's a real life example of finding the area between two curves.
oh, a real life example. Probably not with this particular parabola in this line, but if this blue line is the revenue line, and this red line is the cost line, then the area between the curves is profit. Yep. All right. What do we got? 9 minutes. We should be able to get this example done. Hi, Vicki.
Hi, Mr. Fedor.
How are you?
Good, how are you?
We're doing area between curves.
Oh, that's the funnest. This.
Better than volumes of revolution?
Oh, well, you put it like that.
The Taylor series?
Way better.
Yeah. Way
Better
better
than the
than
McLaurin series. I'm gonna
McLaurin.
shoot myself with series. Bad.
McLaurin series really isn't that bad.
Shouldn't say how to have for you. Yes, she did. She was fine. Oh, I'm sure.
All right. So, let's find the area between the graphs of y equals 2x, 2 cosine x, and y is equal to x squared minus 1. Calculator? So I guess we will use a calculator. I'll allow it then. So here's a calculator. Always in front. And let's. All right. So what are we going to do with the calculator? How's this going to help us in this particular problem?
Draw the two graphs.
Okay, we'll draw the two graphs. All right. Y equals 2 cosine x, and y squared is equal to, or y is equal to x squared minus 1. Oh, I hate when I do that. X squared arrow, that gets me back down there, and then, Anthony?
How do I get the slope bill off my graph?
Typically what happens is when you redraw a new graph, it will, I think if we, like, I'll put it at 3 for just a second, and then when it redraws it, we got rid of this little field. I would use Zoom 6. All right, so there's our graph. Now what?
Find two intercepts.
Okay, first of all, let's acknowledge which is the top curve, which is the bottom curve.
Cosine's the top curve.
Cosine is top curve, we all agree? That it has the higher y values? Higher y, high, the y values are bigger. And then down below is the parabola. Great. So that will help us. So we are going to be able to say then the area is equal to the integral from a to b of cosine, or say 2 cosine x minus quantity x squared minus 1 dx. So we're part done.
Find the intersection.
Find the intersection. So, in the previous example, we took the two things that y were equal to, we set them equal to each other, and we came up with that equation. Well, we came up with a different equation last time. This is the equation for this time. The right reaction to that equation, of course, is it's got a combination of polynomial and trigonometric functions that we do not like. Yes, sir.
Is there an identity that has 2 cosine x plus 1 or
I can, if you wanted me to, convert cosine into a infinitely long polynomial, but we don't want to do that today. What we're just going to acknowledge right now is that using normal algebraic methods, we got nothing here.
Would you rather catch a bowling ball in your teeth?
Or you must calculate the intersection.
Actually, I stole that joke from someone, catching a bowling ball. There's a whole strain of jokes that I'd really like to, no, what I'd really like to do is catch a bowling. Well, there was in that same vein of jokes, there used to be a movie reviewer for Channel 4 whose name was Davy Marlin Jones. And he was a sort of gruesome looking guy. And so an alternate version of that joke is, I'd like to do that. No, I think what I really like to do is win a Davy Marlin Jones look-alike contest. He's dead now. I'm just saying he can't take offense now. Davy Marlin Jones.
Oh,
He
sure.
was a movie reviewer for Channel 4 in the 1980s. All right. So you can change it now to like Ernest Borgnine or who? No. All right. So we need A and B. Where are we going to find them? Second calc. Let's do it. Let me zoom in just one little bit so we get a better look at what we're. Oh, come on. Zoom didn't work. Graph. Zoom. Oh, zoom in is what I meant to do. Zoom in. Okay, let's find the intersection point down the left-hand side. Second calc. Intersection is option number 5. I need to get past. I gotta get lower than that intersection. I'm going to guess that -2 gets me lower than that That was odd.
It's not doing bounds, you just have to move over.
Why wouldn't it do bounds?
Because you're just selecting the curves, you're not doing bounds for
Oh, because I meant doing things in the right order. I want to find the intersection. First curve, enter. Second curve, enter. Now, my lower, I'm going to guess -2 for my guess.
It's just
Well, because there's multiple intersections, how do we specify that this is the intersection that we want as compared to this intersection on the right-hand
kind
side?
of move to the left when you want that one.
Yeah. And so we find that the x value at that intersection is -1.265424. And how many digits do I want you to write down? All of them. All of them. Hey, let's go find the other intersection.
It's the same. It's just positive.
It's the positive version because both of these curves are symmetric about the y-axis. The term I was looking for was even. Okay. Now, trick. Second quit. I'm going to have to do calculations with that value, that negative 1.26 blah, 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 blah.
It's curly square.
Okay. After I find the intersection, after I leave that screen, that number is actually still stored in the variable x. And if I want to, I can take the variable x and I can set it aside in another variable. Or I can take the opposite of x and set it aside in another variable. And then I can use those variables in my calculator when I do the calculations. All right, we'll pick this up tomorrow when the sun will come out. Yes, I do.
How did everyone do?
Low 90s or high 80s.